we have truly exciting times in Huntington's disease, because 26 years after the HD gene and the HD mutation was identified, there is a silver lining on the horizon. And the silver lining is that a special type of therapy that goes to the root of the problem, gene silencing, should be, all right, and is reaching patients. And there are currently 4 trials of gene silencing ongoing, and I'm going to tell you how this is intended to work and where we are. The first study has been completed. That's a phase 1 study. That's safety and tolerability. And a so-called phase 3 study that is about proving that something is working and having an impact on people's life just started. Yeah? So it's, I believe, a truly exciting development overall. And the compound that is going to go into a phase 3 study, and has just started, it's called the Ionis Huntington RX, now with a new name, because it was taken over by Roche and Genentech, 6042. You don't have to remember the name, but just that's the name for it. And as many of you, I suppose all of you, have heard, there is an effect of the compound on the levels of mutant huntingtin in the fluid that surrounds the brain and the spinal cord. And you will see the data, and we can discuss that as we go. The implication of that is that there is tangible hope that finally we will be in the position to change the progressive course of Huntington's disease. Yeah? And that is different to all the other therapies that were explored in the past. It mostly had the intention to improve signs and symptoms, but couldn't reasonably be expected to change the course of the disease. So, what I'm going to do is I'm going to talk about some insights into how Huntington's works, the mechanics of Huntington's disease, if you like, because I want you to understand that there is a lot more in the pipeline. Yeah? And that's important because obviously not everybody can take part in the first trials, but you need to understand that there is far more to come and that there are multiple entryways to participate in that type of research and in exploring what of these therapies is going to work. It's still hope for tomorrow because it's in clinical testing, and there are 2 things that I'm going to talk about, so-called gene silencing as a modality, so shooting the messenger, if you like, as an approach. I would like to explain to you what the ideas are, what the principles are. I'll give you a couple of examples, and then also talk about gene editing, that is, getting rid of a genetic alteration to start with. That's for the future, and there's a lot of hype about it, but also some hope. So I want you to walk away from today's meeting with an understanding of what is realistically to be expected in the next couple of years, of horizon of 5 years. Then I will conclude with help for today, because I think that's truly important. It is very important that we have hope for the future, but we also need to address the problems that we have today. And I'm going to briefly allude to this in the second talk. We'll focus on that in particular. All right. So let's start with the insights into the mechanics of Huntington's disease, how Huntington's disease works. So don't be too concerned. You have seen many of these things. That's the Huntington disease gene. It's on the short arm of chromosome 4. It's a long gene, the Huntington disease gene. And here in this first exon in red, you have the change, the mutation. And as you all know, it's 3 bases, C, A, and G, that are too much. And that is the root cause of the problem. because it's in the so-called first exon, it's translated into a protein. CAG codes for one amino acid called glutamine, so you have a long stretch of glutamines in the resultant mutant protein. Yeah? That has been, the structure of Huntington has been clarified last year. It's a big step forward. So you can crystallize it, you can know where every part is, and that's going to be very important going forward. Yeah? That we know this. What you all know is that there is a relationship between the number of CAG repeats and the age when you get Huntington's disease. So this is shown here. If you have a lot of CAG repeats, you get Huntington's disease signs and symptoms early, even as a child or as a youngster. Yeah? And if you have a lower number of CAG repeats, it may be very late, even in your 80s, yeah, that the first symptoms and signs appear. So that's important to keep in mind and to be aware. The way we used to think about Huntington's disease is because it is translated into a protein, that that is the core of the problem, everything happening at the protein level. And the idea is that's true for other neurodegenerative diseases like Alzheimer's disease and Parkinson's disease, that you have this polyglutamine chain extended on a mutant Huntington that is cleaved off and is forming clumps of protein inside the cells. And you see this, if you look under the microscope, as a proteinaceous deposition in the cell nuclei. That's a conventional way to think about this, and where a lot of efforts have been focused on. It's important, though, for you to realize that it's obvious that it's not only the protein that is changed, it's also the instruction to build the protein that is different. This is called messenger RNA. Yeah? And this comes in two flavors that's going to be important later. One called pre-messenger RNA, where you have not only the instructions for building a protein, but also things here depicted in blue. Can you see this? Yes. Yeah. You can't see my cursor though. Can you? No. No. So in blue, are parts that are cut out. Yeah? And the proper building instructions is in other part of the cell. Yeah? This is going to be important later on. If you have more CAGs, you see this hairpin, yeah, as a result, direct result of the building instruction being different. And this hairpin has consequences because the building instruction inside the cell is interacting with a lot of things inside the nucleus of the cell. For instance, it can result in not only a protein that has a lot of polyglutamines, but it can also result in 5 other proteins because of an unusual way it is translated into protein. So it's not one protein only, it's 4 additional proteins that are produced from this. This is a new insight that we learned. It's also possible that the process where you get rid of what I showed you in blue, the ins or introns, called splicing, cutting that out, is altered. And the result of this is that the very first exon may be produced more abundantly and exclusively with the mutation. You can imagine that that has impact. And Jill Bates, who many of you know, working in London, has been working on this and focusing on this as an important component. No? So potentially of the disease. And then you have, all this is the result of the building instruction, the messenger RNA, acting in an abnormal way, having this hairpin. Yeah? And likewise, this hairpin interacts with so-called RNA binding proteins, or RBS. This is depicted here. You see these colorful blocks over there, RNA binding proteins. If they interact with the building instruction, with the long poly-CAG stretch, they interact differently, they get trapped and are no longer available. And that has consequences. You can see this in the cells. If you look at cells, you see these bright spots. And these bright spots are not normal. They are only there if RNA binding proteins are trapped. That's quite important because there are other disorders that have their root cause in changes of the RNA binding protein. So forms of Lou Gehrig's disease, ALS, and are caused by this. And they also go along with a change and loss of nerve cells in the basal ganglia, the part of the brain where a lot of the damage is in Huntington's disease. Yeah? So these things are related in an important way. So it is important for you to realize that it's not only polyglutamine expanded Huntingtin, it's also the other protein products that do damage. It's the misfolded building instruction, or mRNA, in the cytoplasm, as well as the pre-messenger RNA in the nuclear compartment. They all work together to inflict damage. So if you want to intervene early, you have to go ideally to the pre-messenger RNA, because that is abnormal already, and then and only then you can prevent other things from happening. Is that clear? It's complicated, but I want you to understand this because it helps to appreciate what is done in terms of therapeutics. All right? Okay, good. So obviously, at the core of the problem, however, is that the DNA is changed. You have more C, A, and Gs. And let's focus on this for a second, because that's equally a very important component. Here, you can see on the left-hand side, if you inherit Huntington's disease from your mother, it is very likely that as son or daughter, you have the same CAG repeat length. If you inherit it from your father, it could be the same, or it could be larger. This is depicted here on these red dots upwards, squares upwards. Yeah, it can get larger.
So it's different maternal.
Yes, yes. And so if you get it from the mother, it's likely to be identical. If it gets from the father, there's a chance that it gets larger. The CAG repeat expansion gets larger, and that is happening in sperm cells, as sperm cells are built. Yeah. Now,
what percentage of people in the fathers, how much does it vary?
Mm-hmm. It varies quite a lot. So let's go back. You can tell this is the majority of people have it identical. It's about a third or so, 25, a third
so
that have
75 have similar. So
yeah. Huh? So the rule is it's similar, but it can get larger, and it can get smaller too. That is happening too, although more rarely. But there can be big jumps. That's what I wanted to get across to you. It's a difference. Now, we know this from sperm cells, and the interesting question is if the size of the CAG repeat tract can be unstable in sperm cells, is that true for other cells of the body as well? And the answer is yes. During life, the number of CAG repeats can increase. So if you have larger CAG repeats, they can get even larger during your life. It's dynamic. Yeah?
It's not stable.
It's not stable, and to what extent it's unstable depends on other genes, as I will explain for you. But that's important to realize. It's not stable, it has the tendency to get larger. If you look at brains of people who died from Huntington's disease here, and you see that if you have in blood 51 CAG repeats. It can get up to 700. Yeah? It's a lot more. In striatum, as part of the basal ganglia, the part that is particularly vulnerable in Huntington's disease. Yeah? Or in the cerebral cortex here on the left, you see in blood 87, which is a lot to start with, but it can get to way above 400. Yeah? It's important to realize it's not identical, it's not stable throughout life. And if you look in animals that have the Huntington disease mutation, mice for instance, you see in certain regions, for instance here striatum, you see a lot of blue bars to the right. Yeah? There's the peak, that's what you have in blood, and to the right is longer repeats, and the frequency is displayed here. Yeah? You see, it's quite a lot, yeah, in animal models now. But I've shown you that is happening in humans too. Now, if you look at cortex, and another special part of the cortex, hippocampus, it has to do with your memory, you see something to the right, less high than in striatum, less frequent, but it happens there as well. There's other parts of the brain, cerebellum, here in the back of your brain, seems to be stable. So it's not equal, and it's happening primarily in the brain, and it's in particular regions, and are those regions that are particularly affected by Huntington's disease. Yeah? It happens also in other parts of the body, in the liver. The liver is not known to be affected in Huntington's disease. So that's interesting that we learn that in liver there seems to be similar changes without them having the same consequences of destroying the function or compromising the function of the organ. Yeah? All right. So now, researchers have looked what type of cells within the brain display that expansion. They're the nerve cells, and there's the support cells called glial cells. And if the nerve cells do not divide, and interestingly, it is happening in the cells that do not divide. That's surprising. You wouldn't have guessed this. We, the researchers, didn't guess it either, that it would be like this. Yeah? So the non-dividing cells, the nerve cells, show this expansion of the CAG repeat tract. Everything very dynamic. So the conclusion from that observation is replication of DNA, like is required for all dividing cells, is not necessary for an increase of CAG repeat expansions. So what then? Well, it is, and I'll give you an answer for this, but I would like to remind you what the big questions are for us to understand Huntington's disease. We all know that we are born, if we have the Huntington disease mutation, from the get-go with the expansion. But it takes years, even decades normally, for this to have any effect. So we need to understand that. And likewise, you have the HD mutation in all cells of the body, but it's some cells that are far more affected than others. So how can we understand this? And we have learned quite a lot from experiment of nature, that is so-called genetic modifiers, other genes, aside from the Huntington gene, that are interacting. And what big studies that are only possible due to registry and enroll, where many of you, I guess, here in the room have participated. More than 9,000 people were required to show that these genetic modifiers help us to understand that. Here's again what I've showed you before. The relationship between the size of the CAG repeat and the age you have signs and symptoms. But you can easily tell that with each given size, there is a lot of, this is with the red arrow, a lot of variability. Yeah? And this variability has two main causes: your other genes and how you live. Yeah? These two are the main causes of the variability. Now, if we look at the genes and identify genetic modifiers, then we realize that they all cluster together in one group of things, so-called DNA repair genes. Everything, our bones, also our DNA, are changing during our life. They're constantly turned over, constantly repaired. Every usage of a gene implies that there is the potential for damage that needs to be repaired. And it appears that it is in the process of the repair that the CAG repeat length can increase further. Yeah? It's an unusual insight, but important insight, and I hope it's a complicated story, but I hope I got it across relatively clearly. Are you with me? Yeah?
Can you just repeat that again? That in the repair?
In the process of repair of DNA damage, there is the potential that the CAG repeat stretch gets longer. You can explain this, but it's rather complicated because you need to understand exactly the machinery. But take it like that. In the process of a repair, there is the potential for error, and the error implies that things get longer. Yeah? That explains why you have in brain or in other parts of your body even longer increases of CAG repeats as you age. Yeah? And what we hypothesize is that this fact, this what we refer to as somatic instability, the further increase of CAG repeat sizes, is the driver for the progression of the disease and the driver for the onset of the disease. That is and I'll show you a model in a second that tries to tie it together and explain why the disease starts late and why it is that the disease varies in the rate of progression. Yeah? So the model is like this. You're born with a certain CAG repeat length, and this is below a threshold in red for a long time. During that time you are healthy. Then some cells cross the threshold, yeah? And you have very subtle symptoms and signs, very subtle problems, and then you have real disease above a certain threshold, and at the end stage the majority of cells has crossed that threshold, and you have full-blown end stage damage and disease. Yeah? So, as a consequence of this insight, what we would now that we understood that it is entirely dynamic how long the CAG repeat stretch is, we may think about contracting it. If it can expand, it could also contract. And there's another disease that doesn't affect the brain to the same extent. It's called myotonic dystrophy, for which this has been shown. It's also caused by a CAG repeat expansion in another gene. And for that disease, which affects mostly your muscles, it can be shown that medication compounds can help to contract the CAG repeat size. Yep.
How do we know that contracting the CAG repeats won't affect other genes involved?
It could affect other genes. And you mean by the intervention, by the compound? Yeah. And it could, and that needs to be checked. And it looks, however, as if you have to be beyond a certain threshold for this phenomenon of expansion, somatic expansion, to occur with high frequency. And therefore, the impact of your medication will mostly affect genes that have too long of an expansion to start with. Make sense? Yeah? So this is early days, and the compound that has been developed, yes, please?
Would it be possible that somebody, let's say at 18, got a test
Mm-hmm.
and they were told that they were under, let's say, 36 tag repeats, and then when they got to their 30s, they're told they don't have Huntington's disease and won't get it, and then when they got older, they could have another blood test, and then they could be told, because DNA is repaired in a way, they then could have it. So they thought they were okay, but then
Right. That is not going to happen. The reason is that it is only above a certain threshold that this somatic expansion occurs. Yeah? So you're safe if you are below a certain number of CAD repeats, but once you're past the threshold, so as you all know, it's 36 CAD repeat, above 40 you have full penetrance. That is, if you have 40 and more, you will, if you live normal lifespan, you will develop the disease. So it is above this threshold, and only above the threshold, that you will have this expansion. Yeah?
Is the age and diagnosis of your cagropete, is there a correlation as to when it becomes symptomatic, or I'm a bit confused around that? But if the cagropete, at 19 years of age, it's 55, what's the expectation around?
Right. So based on observations, we have a guess, but the guess comes with a high confidence interval. So because of the other genes that you have, and if you have the misfortune of having genes that are that you have an over-efficient DNA repair, which is good for other things, protects you against cancer, for instance, yeah? There is the chance that you have a larger increase of the CAGs and therefore more severe disease than other people. And lifestyle has an impact too. For instance, if you have a lot of DNA damage, yeah, because of your lifestyle, and that can happen. Then there's more need for repair, and therefore there is increased likelihood that expansions occur. Please.
I wasn't aware of Huntington's. I had been visiting two cousins who had it, but didn't think I'd ever get it. But when I was attending Beaumont Hospital, they did a test on me, and I have it. And this is my sister, and she is waiting to have the test. I had the Huntington. She's waiting to have the test, you know. Or we're going to. Well, I had the test. I'm okay, but I said I would keep up with, you know, the children's hospital, because they want to keep up about get that up. Now the fact that I got it late in life, say I must have been 73, and I think was that a bit of a bonus? I wasn't aware, you know, that
Right.
I
Well,
never get it. Only I just happened to get the test, and it just gave me more hope, you know. And
Right.
my true cousin, first cousin, and I used to visit him.
No. I think if the disease starts late in life, that's advantageous, and it's a reflection of a relatively small CAT repeat. The decision of each other family member to get tested or not to get tested is very personal. Whether you can live with knowing, or whether that's too big a burden. So everybody is on him or herself to make that decision. Very important. Yeah?
Can I just
Sure.
ask you, just to elaborate, you keep referring to lifestyle.
I'm going to expand on this a little bit later.
Okay.
So, yeah. But first, here, what I want is to get to you the concept. Yeah? And this is a new and exciting thing, and I think a pretty exciting insight, that the expansions in DNA are something that is dynamic and can even contract, and for the future may be a target for interventions. Yeah? That's what I wanted to get across. Yeah? That's for the future, more distant future. A lot of research is still needed to have compounds who actually do that job. Yeah? What we are doing at the moment is a thing called gene silencing, and I'm going to explain to you again what that is. It's a treatment that you could apply to all genetic diseases that are dominant in nature. That is, where the mutation implies that something new comes on that is detrimental, and where you would benefit from silencing, dialing down the causative gene. Yeah? Make sense so far? And the way you do this, and the way how we do it, is that we interfere. That's why I explained to you about the building instruction, the messenger RNA, at the level of the messenger RNA, or the so-called transcription. You want to reduce the number of building instructions or messenger RNA, and as a result, you have a lower production of all the other gene products, including the protein. Yeah? And you measure whether you do this right by looking at the protein. Yeah? Okay. And luckily, we have a number of tools to do that, the gene silencing. And you will understand that even better later. It's the antisense oligonucleotides, or ASOs. These are pieces of DNA, and I'll show that to you how this looks like. There are RNAs that can bind to the building instructions and degrade them, get rid of them, and therefore impede the further production. Yeah? And you can use zinc fingers. These are just words, I'll explain it to you. And small molecules. So at least 4 categories, yeah, of tools that we have. Yes, please.
Sorry, by zinc finger do you mean caspase 9?
No, the zinc finger proteins, they could be used also for gene editing, but as I'll show you a little bit later, they're used in conjunction with a repressor to silence a gene. It's a different type of technique. You'll see that in more detail, and I'm going to show that to you. Yeah? So, important number of tools that we have to do the very same thing, reducing the building instructions and therefore the further production of the mutant gene. Yeah? Okay. So, and it makes sense that if you intervene early in the process, you have larger effect sizes. The earlier more upstream you are, the more likely it is that you have big effects. So, let's look at this. Here is in a gray the nuclear compartment. Yeah? Here is your gene. It's transcribed. A building instruction is built. And you have the so-called pre-messenger RNA. Now you're experts, you know what I'm talking about. So with the introns. Okay. And then the mature building instruction that will be translated into a protein. Yeah? So, antisense oligonucleotides in green, ASOs, are pieces of DNA that bind to the pre-messenger RNA in the nuclear compartment. Yeah? And degrade the number of building instructions. Inhibitory RNA can bind to the mature messenger RNA in the cytoplasm and results in a degradation of the mature messenger RNA. Yeah? Different processes that are involved to get rid of it. Both have the consequence that you have less of the mutant protein. Yeah? But they act, one is earlier, the other is later. So, you can use small molecules that interfere with the splicing process, and by doing so, they can result also in a reduction of the building instructions. Or you can go to the DNA with the so-called zinc finger, and I'll explain that to you, that prevents even the formation of the pre-messenger RNA. Yeah? Get a step earlier. Okay. And then you can correct the genetic mutation. This is, for instance, by Crispr, Cusp, and other techniques that I'm going to talk about. So, but these are categorically different approaches. Some are fiction at this point in time. Some are going to be reality in the not distant future. Yeah? So, the first, as I told you, what we have done is a phase 1 study. The phase 1 study was led by Sarah Tabrizi from London. You know her? She looks pretty nice, huh? Yeah. So, phase 1 study. That's all about safety and tolerability. Yeah? And so, let me show you what I've showed you as a diagram now in more reality. This is the compound that we are using. It is a stretch of DNA, single-stranded DNA, that binds to the messenger RNA, and it has been chemically modified. And that took 15 years. The idea of doing this we had right from the identification of the gene, but we didn't know how to do it right. And to cut a long story short, I'll show you on the right is the chemically modified messenger RNA, antisense oligonucleotide, and what you see is a lot of pink and red. These are surfaces that like lipids. That's important if you compare this to the one on the left with a lot of green. This likes water. In order for this thing to go into the right place, it has to go through lipids. The membrane of cells are made out of lipids. So we needed to learn how to change it in such a way that it can go through membranes in order to act. Yeah? And this took about 15 years to make it safe. So that's it's a complicated, more complicated story, but I think conceptually you got what I'm intending to say. Well, okay. All right. So despite the fact that it passes through membranes relatively well, and it's not going through the so-called blood-brain barrier. So it has to be got to the brain and to the spinal cord by another route. And what we are using is the fluid that is surrounding the brain and the spinal cord. And if you do this, it's called an intrathecal injection. That is a procedure that many of you know from childbirth, for instance, and you do a lumbar tap, yeah, to get to the cerebrospinal fluid. And if you inject something, that's called intrathecal injection. So you get it into the space, the fluid space that surrounds the spinal cord and your brain. And if it's there, it can penetrate through various membranes into the regions where you want it to be. So that's the way it looks then, and it is injected and goes up to the brain. Yeah? So that's what we are intending to do. Yeah? So? Okay. So, because it's a safety study, we went stepwise. And we, as you can see from these various bottles, and increasing levels, concentrations, and step by step, because we couldn't know whether it was safe and well tolerated. So the way it worked is if a small group of people got a very low dose, everything was reviewed. When it was fine, we went to the higher dose level and so on and so forth. That's why it takes time, because we want to go stepwise and be sure that you're not doing any harm. The way we did it here in blue is the injection. So this is 20 milliliter of the compound in an artificial CSF. You first draw out 20 ml of normal CSF and then replace the same thing with a push bolus injection. The idea is that you get it up relatively fast and generate a very steep concentration gradient in order to for it to diffuse as widely as it possibly can. Yeah? Intrathecal bolus injection. So it was a small study, 46 participants worldwide, and it had a placebo arm because so people getting not the compound but something without the compound, because we wanted to differentiate. If you do this several times, the procedure, that could result in some complications too. We wanted to be sure what of the complications, if there were any, and it were due to the compound and which one were due to the procedure. It was conducted in the UK, in Germany, and in Canada, in Vancouver. And overall, we are glad to say it was well tolerated. That's definitely good news. with repeated lumbar puncture, one of the complications is that you get headache because there is a leakage of the CSF later. For that reason, we take a very, very thin needle. And doing that, the number of headaches were low overall. So it was well tolerated from that perspective as well. And that's a very important result. No serious adverse effects, no other changes in the laboratory as well. Yeah? And that's the main result. You see here that mutant Huntington, which we wanted to reduce the production of, indeed got lower. In gray you have placebo-treated people, and in green you see the decrease. It's up to 60% decrease in the production of mutant Huntington that we could measure. It's quite an effect. And to be quite frank, I was part of the study. I was surprised that we had this clear dose dependency. It was a pleasant surprise, of course. Yeah? And so, there are questions though. I mean, it's very nice to see that decrease, but do we reach all parts of the brain that we need to reach? Do we reach the striatum where there's a lot of the damage, and do we reach the lower layers of the cerebral cortex where the neurons are situated that project to the basal ganglia, to the striatum? That we don't know for sure, and very important, of course, does the treatment bring about clinical improvements? This was a short study, as I alluded to. So too short to be sure, because it's a slow disease, as we all know, and to know about that. And at this point in time, we don't know whether we are, at this point in time, slowing the rate of progression and whether signs and symptoms improve. A lot of people that I have treated, we have treated 9 people in the context of this study, have improvements. But that's in part because you're hopeful. You're mobilizing your energies for obvious reasons. So it needs to have a controlled study to prove this beyond doubt. And of course, the big question is, do we reach enough of the brain? Here I show you a model that is a model calculation. If you have a reduction of 40%, you have in cortex, in the tissue. We are measuring in the CSF, but we want to know what is happening in the tissues for obvious reasons. So it's quite an impressive reduction in cortex. And if you have, as we saw, a reduction of 60%, even in the deep parts of the brain in cortex, you have a reduction of about 50%. So that instills some optimism in us that this will translate into what we hope for. That is an impact on progression and an impact potentially, hopefully, on clinical symptoms and signs. Yeah? Okay. And we know from animal studies that we need 30 to 50% reduction for a behavioral effect that allows us, to a certain extent, to predict clinical improvements. And we looked into this. So here is clinical outcomes, and what you see here on a y-axis there is a clinical on a scale which is called composite UHDRS. It's a combination of motor science, cognition, and function. And what you see is here on the x-axis a reduction of mutant Huntington. And you see in gray placebo-treated folks, and in green folks that are treated with various dosages. And you see that there's a correlation, not an extremely strong correlation, but you still see that there is a relationship. As expected, most of the gray points are to the right, and most of the green points are to the left, so associated with some clinical improvement. But obviously, we have still questions. For instance, if you treat longer than 13 months, as we did, what are the effects? Important question, is that having an impact on the progression of the disease? And are there any safety concerns emerging? Because remember, and I didn't stress this before, we are lowering both flavors of Huntington's disease, the normal as well as the bad, the mutant one. Yeah? So is that well tolerated on the long run? That needs to be established. And also importantly, we inject it every month, which is a lot of injections. Can you do with less? Yeah? That would be advantageous, of course. So all these things are going to be addressed with Roche. From the 46 volunteers, we are now moving to a far larger program, 660 people that are going to be examined in a so-called, in other studies, an open label extension, a control to the open label extension called natural history, and most importantly, a phase 3 study with 660 participants. And that will go over 2 years in that many people, and will hopefully answer the question whether it has an impact on the progression and has an impact on symptoms and signs of Huntington's disease. So there are 2 dose arms.
Sorry, that
Yep.
study, will that be over, will that, will it have a range of ages?
Yes,
Groups?
it will have a range of, so the inclusion criteria are listed here. So you have to be between 25 and 65 years, and you have to have clinical symptoms and signs of Huntington's disease and the genetic mutation, and it has to be of a certain intensity. And this is called CAP score. That's a technicality, and and you have to be able to be walking into the clinic unaided, so ambulatory, and you have to be able to communicate. These are the inclusion criteria, and it will be now, and that has been changed relatively recently, every 2nd month an injection, every 4th month. Yeah? So it's less intense than what we did in the phase 1 study, and the reason why we could do this, or feel we can do this, is that the reduction in mutant huntingtin that we measured in an open label extension with a 2-monthly injection was as good as with the monthly. Yeah? So sufficient a reduction so that we can think, that we believe it is possible to be less frequent. Yes, please.
In your screening criteria, if people are on some medication, say tetrabenazine, does that rule them out?
No, they have to be on a stable dose of tetrabenazine or other compounds, and there are certain restrictions indeed. Relatively rarely used medications. You cannot take, for instance, a medication that has been in the past explored, whether they can modify the progression of the disease. The very unfrequently used medications are exclusion criteria. Unfrequently used, yes, please.
Are you using different concentrations
Mm-hmm.
with the 600 people?
We are using one concentration. It's 120 milligram.
On what basis?
On what basis? That's on the basis there are a couple of considerations. So I showed you the phase 1 study where we had increasing dosages. The highest dosage was 120 milligram, and we are sticking with this because we believe, it's also based on a model, on various pharmacokinetic models, that a high concentration initially as a bolus results in the most widespread distribution of the compound. Yeah? And this seems to be well tolerated. So there are 2 constraints. It has to be well tolerated, and it should be as high as a concentration in order to increase the spread or improve the distribution. Yeah? Yeah? So it will be one dose, but different frequencies of application, bi-monthly and 4-monthly. Yeah? And this will start with this protocol in June this year in worldwide with 660 participants overall. So it's obvious that there are far more interested people than 660. But we need to exercise judgment. We want everybody who starts the program to stay in the program for 2 years, in order to have sufficient power to say it's going to work. Okay, now that's just one and the most advanced project. And now I'm going to talk about a couple of other projects that are also in the making. WAVE is running 2 trials, currently phase 1 trials. And here the idea is that they use an antisense oligonucleotide that is allele selective. So if it works as hoped, and it should preferentially lower the mutant allele and leave much of the normal allele untouched. Yeah? And the way you can do it is that you exploit variations, genetic variations in the gene, so-called single nucleotide polymorphisms or SNPs. Because that's a complicated concept, I'm trying to explain that to you. Imagine mutant Huntington is a red balloon, yeah? And wild type normal is a blue balloon. And what you are targeting, you want to shoot this down, yeah? So what you're targeting is not the blue balloon, but a ribbon in the tail of the balloon that is unique to this. Yeah? That's the idea. That's the single nucleotide polymorphism. Yeah? And if you are successful, it will go away, and the other one will stay. That's the theory. Yeah? Okay. In order for this to work, you have to establish that you have these blue ribbons on the tail in the first place. And that's not present in everybody. Yeah? So the first step in this is that you establish who has it. Yeah? You have to measure this. And only if you belong to those folks who have this blue ribbon, so to speak, it will work for you. So there is a screening process. And eventually, there are some people, 1/3, we say, we believe, and that will not have such a single nucleotide polymorphism or a blue ribbon that would not benefit from this type of treatment. So the other one is for everybody, but comes with the downside that it decreases both. Yeah? This here has the potential to work selectively or preferentially on the mutant form. Yeah? So it's the same idea. You do a safety and tolerability, and that's where we are for WAVE at the moment. And it's ascending dose arms, same what I showed you, increasing dosages, very careful, unevenly done. Short, like the phase 1 study from Ionis, same number of participants, about 46. And that's currently ongoing in Canada, US, and Europe, and may extend to some more European countries. Okay. So it's important to realize that this principle is used for diseases other than Huntington's disease as well, and with increasing success. So there are 2 other conditions that are treatable through this modality. One is a rare form that is most prevalent in Portuguese people of nerve affection, and a severe form of childhood SMA. Many of you have seen pictures of these kids that are affected by this. So let's go beyond this, though, beyond ASO. What I've described to you so far is not gene therapy. You're not interfering with the DNA at all. Yeah? You're just interfering with the messengers, the blueprints for the production of proteins. Now, let's turn to real gene therapy. So gene therapy implies that you have to get whatever you put in as a treatment modality to the right place. And therefore, we use viruses to get it into the right place. These are viruses that can enter nerve cells, non-dividing cells, and they do not cause harm by themselves, and have been used for a variety of disorders with safe results. And the basic interesting concept is that a single treatment would have the potential that you would have an ongoing production inside your own body of something that treats your condition. So instead of having repeated injections, as I described to you, you would have one treatment, and then for a long period of time, your body would continue to produce it. Yeah? So conceptually, it's interesting, but it requires that you inject it directly into the brain. Here it's showed in a monkey. Yeah? So it requires brain surgery. Yeah? And here you see in brown the distribution. It's injected into the center of the brain, about here, and you can see in the brown that even in the cortex, yeah, you see some brown staining. So it's transported, which is pretty interesting, and it's transported along the nerve cells. So long projections called axons, and there are other, and it can go from cell to cell, in theory. Now we know that in Huntington's disease, the transport from cell to cell may be impaired, so we don't know whether it's working the same way as it does in normal animals that I'm showing you here. Yeah? So this is used by Unicure. Here is the virus, and they're hoping to go into the clinic next year, 2020, in all likelihood. And the idea is that you have the virus here in blue and red. You have what is inside, that is taken up by the cell, going into the nucleus. It's not integrating into the DNA, your own DNA, but it's constantly producing an RNA that is binding to the mature mRNA and degrading it, as you can tell here, and therefore as a result you have less of the mutant Huntington product or the Huntington product overall. Yeah? So that's the idea. The problem is you have to get it to all places. Here is where they are hoping to inject into the striatum, and they're hoping that this is matching more or less the main sites of pathology. They have tried it in various animals with large brain. For instance, here a pig, a mini pig that has the mutant Huntington, and you can tell that in striatum there is pretty decent reduction, also in frontal lobe, but there are other parts of the brain, occipital lobe on the right, where you don't have a reduction. Yeah? So that's the challenge of this type of treatment modality. Do you get it to all the places? And obviously it requires brain surgery. This comes with some complication too. Yeah? So, and then you don't want to overdo it. You don't want to have zero Huntington left, and that's a challenge by this type of treatment. And all these questions still need to be addressed. It's also foreign, so it's a virus. You can have an immune reaction. You can have the potential of adverse effects due to this. Another company called Voyager is using another capsid, another virus, in other words, for the same end. And these programs are going in parallel. Here they're injecting into a different part of the brain, so-called thalamus, that is connected to the cortex as well as to the striatum. And they are hoping, because that's a better preserved structure, that this may result in better delivery. This is up for a test in the following couple of years on what is going to work better in practice. Now, these two techniques will suppress both the normal and the mutants. And now I'm focusing on a technique that is promising to exclusively reduce the mutant copy. That's a zinc finger. Zinc is the green dot that you see, and this is a protein, and this protein, like a finger, is recognizing C, A, and G exactly. Yeah? And this technique was developed by Sangamo, then developed further clinically by Shire, and now it's Takeda, a Japanese company, who's going to do this going forward. So the idea is that if you have this zinc finger recognizing C, A, and G, and combine this with a so-called repressor, then it's obvious that if you have a lot of CAG repeats, it will bind to that a lot. Yeah? And if you have a normal number of CAG repeats or another gene with CAG repeats, it will bind just a few things. And if you have a lot of it binding, you will have a silencing of the gene. It's no longer produced. Yeah? The pre-messenger RNA is no longer produced. Yeah? That's the idea. You're not altering the DNA, you're using the zinc finger protein combined with the repressor to silence the gene. Yeah? That is resulting in pretty good preclinical results, and Takeda is going to move it within the next 5 years into the clinic as well. Same problem, you have to put it into a virus. The virus doesn't go everywhere by itself, so it's a distribution problem whether it's going to be working or how beneficial it's going to be. Now, in addition, we have, and all of you have heard about this, gene editing, that is correcting the genetic defect right from the get-go. It's pretty popular in science, so you see a lot of papers. I'm just showing you a couple of those where this is applied to do it. And so quite a lot of papers, very fascinating. And you have more than one modality. The most popular one is the Crispr-Cusp technique. This is something that is derived from a defense of a bacteria against viruses in principle. And the idea is that it works like you correcting a spelling error on your computer. First you have to find the mistake, then you have to delete the mistake, cutting out the wrong letters, and then correcting the mistake, filling the correct letters in. And what this means for these editing techniques is finding the mistake. You have to have a cursor that goes there. Deleting the mistake, like a scissor, is Crispr-Cas9, and then you have to correct it by retyping. So, and this is the DNA repair machinery. So, obviously, a lot of things can go wrong. The cursor can move to the wrong spot. The scissors cut at the wrong places. The scissors are recognized as foreign, which they are. They come from bacteria. And the repairs overall goes wrong. And because it's your own DNA, this may have consequences that you do not want. And like for the other techniques, you have got it delivered. You have to pack it into a virus and get it into the cell. And that's a general recurrent theme. Delivery is the problem. And we deal with a big brain. We can do this successfully in a mouse brain and in a rat brain. Macaque here is in the works. We don't know yet. And for us, we don't know either. But you can tell it's 20 times as large as the macaque brain, our brain. So delivery is a serious issue. Not the principle. So, I would say currently, correction of single cells or cell cultures we can do already. It's done for certain cancers already. But an entire living organism, or the 100 billion cells in the CNS alone, that's not reality at this point in time. And it will take time to get there. At least a decade before we can know what the place of these things are. Yeah? Okay. So far? Clear? And you see there's a lot of things happening. And that is quite important for all of you and exciting to follow. Yeah? So, we should also, though, be sober about it. So, in the past, if we look at trials that aim to slow the progression of Huntington's disease, we have done this in 8 trials and more than 1,300 patients. A lot of compounds were studied. I'll list them here. And sad to say, as you all know, no study reached the primary endpoint, met the primary endpoint. None of these things worked. So when I was a postdoc, I had this on my laptop. The route to success is to go from failure to failure with undiminished enthusiasm. That's important. So setbacks are to some extent normal, and we need to be sober and aware of this. It's not a given. It's still an experiment. But I think what I've shown you is a plethora of things that are in the works, and so that does give us hope. So therefore, we need also to consider help for today. The attitude that we had in the past is this. This man has Huntington's disease. I have not arranged to see him again. There is nothing more I can do but diagnose it. And that the biggest change in the past decade is that this attitude has disappeared, because it's not true. You can treat a lot of things. The way you do it is you analyze, and that takes time. What is the main problem? And you try to address, for instance, chorea or other problems that are in red. Things that are in green you keep, and the things that are in orange you think about what to do. It's clear, though, that there are limits. You can improve things, but the disease will progress. And that's what we are hoping to address that problem with the upcoming therapies. That's why we need research. That's why we need to work together. And that's the European HDAs, stronger together, very true. And that's why we have big studies. As you may know, in December, more than 20,000 participants are in enroll. And now, and we are going per month, more than 300 new participants worldwide, which is pretty impressive overall. So that's excellent. We have now, we believe, a solid foundation. You know, we don't want this. This is Italy, although this is Switzerland. I mean, it's supposed to be a solid country, but well, you have to get the foundations right. But the record worldwide is this one. This is in Germany, so not that solid. So we don't want this. And we feel that we are no longer painting a bird looking at an egg. We are really moving towards depicting reality as we go forward, and not only aspirational. Yeah. So it will take time, though, because the studies are beginning, until we know what is working and how well it is working. So what can you do in the meantime? So one, that's coming back to environment. So getting in the best possible shape, the role of your own activity. We are running, together with colleagues in Cardiff, a trial where we look at one flavor of this, staying active. Yeah? Physical activity in Huntington's disease appears to be associated with better outcomes overall, but that's not easy to do. Yeah? So the root cause why that is that we believe a lot can be compensated. And that's true for each Huntington's disease patient, because for decades, despite the fact that there is damage, you can compensate for it. That's due to plasticity. And we want to explore what type of exercise is best to keep your brain plastic and to keep it in the best possible shape. And it needs to be sustained. Therefore, what we are exploring, because the own activity is in demand, is to see whether you having a personal trainer working with you for a year makes a real difference, or whether the fact that you do keep a diary and do it on your own pace, it results in better outcomes or inferior outcomes if you don't have the support by somebody who is trying to motivate you, controlling you, and keeping you on the ball, so to speak. Yeah? So we are doing this also in upcoming JP&D, Joint Program of Neurodegenerative Programs. This is a multi-domain lifestyle targets for improving prognosis in Huntington's disease. This is done with colleagues in Cardiff. Madeleine here from Dublin is part of this. Spanish colleagues and colleagues in Switzerland and in Poland, as well as ourselves, we are contributing to this. And we are developing Healthy R&D, that is an electronic platform that is going to help people in various stages of Huntington's disease, and a Healthy R&D, European e-healthcare model for rare neurodegenerative diseases. We all know that experts are in high demand and not available everywhere. So we are exploring whether using internet and other techniques helps to get the knowledge both to professionals as well as to families. And this is done also here in Ireland. And Jennifer is an important component of this particular program here. Yeah? So this is on the horizon going forward. So, and I believe we need to get the balance right. It's important that a lot of people contribute to research and take part in this, but daily life has to work as well, so help is needed. And what we want you to is not only to get on the bus, but also behind the bus and push, and in particular if the conditions are harsh, like here, and I thank you for your attention.